hello. Okay, it's recording. Let's start. And I begin by bringing up my daily lecture summary. And so I have put here the color background convention, but I have not had a chance to talk about that last time. So let's see. Yeah, I have reproduced it down here. Okay, so basically the green color is what I covered during the current lecture. So at the end of the lecture, I would change the background to green. And the magenta would be what I had covered in the previous lecture. So that way you can follow the progress. Okay. And meeting 2, my handwritten note from Friday, let me bring up for everyone to see. So you see from the question that a student asked, probably, I should have noted down the name, maybe Kyle or, yeah, Kyle, right? Was it Kyle's question? Yeah, I would like to also put the face and the names together. Okay. Kyle asked about the meaning of the damping coefficient. Okay, you see that at the end of class I added my annotation to my handwritten notes, so that very detailed. You see, I not just the formula, but explain each of the variable or functions in the formula. Fk, Fs is just another possible notation, with S being mnemonic for spring. But I think with the subscript K, that will be consistent with the notation for F sub C, the damping force or the damper force, with C being the damping coefficient, and it is proportional to the velocity. Okay, so the spring force is proportional to the displacement or the stretch. You have an equipment to exercise that you have to stretch, right? So the larger the displacement, the more force you have to put in. So what would be, so that's the physical meaning of the spring force that everyone knows many years ago. How about the damping force? Why is it proportional to velocity? What's the physical meaning? Could someone provide? Robert?
It could be like,
okay.
Sorry.
Go ahead, and I'll pick up Kevin. Go ahead. Okay.
It could be like friction or air resistance, things like that.
Friction or air resistance, yeah. So how do you say that? Maybe Kevin can add something.
It's just like, I think about like a simple dash pot. Like the faster you push into it, the harder it's going to resist you.
Yeah. So or air resistance or the car, right? Actually, the optimal speed to save gas would be around 55 miles per hour and 60 miles per hour. That's why, during the oil crisis in the 70s, the speed limit was set to 55 because cars are designed to be optimal at that speed. So yeah, any of the viscous damping for the door, if you try to open very fast, then it's more resistance. Right? So that's the physical meaning. Yeah, so it's not just formulas, but you need to be able to feel the meaning of the formula in your bones. That's much better. Okay, so I think we if I need to bring up, I mentioned. And one thing that I would like to mention is that the advice to if you need to write in order to stay focused, please do so. Feel free. Okay, this is the advice that I mentioned before is probably for people like me who cannot split my brain, one part writing and the other part listening. I don't do that well. Okay, so it's a special condition for me. If you feel that, do whatever you feel comfortable to focus and participate. That's great. Okay, so let me see here before I forget. All right, so let's continue with so the goal. Okay, the goal of this section and what we are doing. Last time I introduced the 2 degree of freedom spring mass and damper system. But I need to mention something before we go on. We can easily go on and develop equations of motion and things like that. But let me pose another question here. What is this? What is the connection between this 2 degrees of freedom model and the Akashi-Kaikyo bridge? There's a very, very close connection. Kai?
Is it that I forget what it's called, but they had the hydraulic system that was the dampener for the swing?
Yeah, okay, so, Kai, remember, you remember everyone laughed about when the workers moving periodically at the top of the tower and the damper, and the fact that the damper would reduce the amplitude of the vibration. Okay, but here, another way you can think, and I don't expect, many students would relate to this yet. So here is a quick explanation, and this is related to finite element as well. Okay, so if you have think of the deck of the bridge as oops. I meant to draw a straight line. Okay, so this represents the deck of the bridge. And let's say if you look, wave propagation in earthquake engineering also fits into this model. So if you think of the deck of a bridge as a continuous system, and you model in finite element, okay. So essentially, what does it mean? It means that you chart this continuum into elements, small elements, and let me represent just very quickly by these red lines represents the nodes, the finite element nodes, and need not be equidistant, need not be uniform discretization. Okay, but let's say you can have something like this, and it can have millions of elements. The more elements you have in the model, the more accurate the result. Okay, so each of these elements here working only in the axial direction. Just only consider the deformation in the axial direction, like an elastic ball. Okay, and when you formulate the finite element model, each element here can be represented by a spring. Okay, and there's a spring constant that is related to the Young's modulus, the area of the cross section, and the length of the element. Okay, maybe let me just write it down here. So if you think of this element or a typical element E, right, with the Young's modulus, E can be, each element can have different material property, right? Different Young's modulus. So the superscript E in parentheses is just to mean that this Young's modulus is part of element E. Okay, and then you have the area of the cross section. That's A, E, and the length of the element, and denoted by capital L, E. Okay, so the length is essentially can be represented here. You know. Right, so that's the length. That's easy to draw. Okay, I can rearrange later. So the spring constant can be easily derived from mechanics of materials. How many of you took mechanics of materials? Yeah, all of you. Okay, so you may have seen this derivation before. Let me leave an opportunity for someone to contribute before I write the formula. Essentially, what I want to write is the equivalent spring constant in terms of the Young's modulus, the area of the cross section, and the length. Do you remember somewhere, Kevin?
EA over L.
Yes, EA over L. Very good. Yeah, so K is written as the Young's modulus. Okay. E. So that the shape looks identical to you. Easier to read. Okay. And divided by the length L. So physically you can see that the spring constant would be higher if you have a stronger material, meaning higher Young's modulus. The spring constant would be larger if you have a larger area of the cross section. For example, a cable on a suspension bridge, the larger the diameter, the stronger the cable. And inversely proportional to the length. For a longer element, the spring constant would be weaker. Okay, so that's physical meaning. Okay, so with that, I have connected the Akaishi Kaikyo bridge to this model. So this is a very, very practical. This is an application of what we are doing. You know, so it's not just mechanics and mathematics without any application. Here we take three elements because we want to simplify the problem so that you learn the method of solution. But the same method of solution is applicable even when you have hundreds, thousands, millions of elements or degrees. Another thing is that I was talking about the spring constant, but you can also have damping in each element. So this model here provides you also damping. Okay. So the goal of what we will be doing today and the next few days is to derive the equation of motion. Okay. Once you have the equation of motion, then we go to the next step, how to solve the equation of motion. Okay. So that's the goal. And let me give you the result first. We want to arrive at two coupled linear second order ODEs, ordinary differential equations, with constant coefficients. Okay. Now in differential equation, you learn about a single or scalar linear second order ODEs with constant coefficients. You learn how to solve that, and I have also review material in the course site. And so here we have a system of two coupled linear second order ODEs. Okay, that is new, totally new. And then the solution, the method of solution will lead to the generalized eigenvalue problem. That's also a new concept. And how you combine the separate solution into the final solution of this coupled system, that's also new. Okay, so that's basically essentially the plan there. All right. So how do we proceed to derive the equation of motion? You know, dynamics is basically very similar to statics. Okay, the only thing that you have added to statics is Newton's law, F equal ma, force equal to mass times acceleration. Okay, but otherwise the method of derivation is identical in principle. So let's forget about static for dynamics for now. Just think about static, right? Think that you have this system subjected to two applied force, okay, F1 and F2. How do you solve this problem in statics? Not even talking about dynamics. Free body diagram. Okay, and that free body diagram is really a breakthrough in the around the time of Euler. Before Euler, it's not possible to do this because Euler introduced what is known as the cut principle, Euler cut principle. Okay, what it works is as follows. Because without Euler cut principle, there's no statics, no dynamics, no nothing. Okay, because of the Euler cut principle, and the principle states as follows. If you are given a system, right? If you cut off the supports, let it undergo free. That's why it's called free body diagram, right? So you have to replace at the cut the internal forces, and so that whole system, whole structure has to be in equilibrium. That's number one. That's the global equilibrium. And then you can perform the cuts in many different ways. You can cut each element out, right? And you can isolate the mass, or you can cut a substructure that includes two elements. Okay, there's many different combinations of subcomponents or substructure that you can cut. But however you cut, the principle says that each subcomponent has to be in equilibrium. Okay, that's the Euler cut principle that you learn from statics. So now, this problem here, note that it is in one dimension. Okay, it is a one-dimensional model. There's no motion in the vertical direction. So if you have problem of picturing the motion, think of the mass is supported on rollers, so it's only move this one. Okay, it does not move up and down. Okay, no vertical motion, only horizontal motion. Okay, so keep that mental picture in mind. Yeah, so this is the first cut. In this. Yeah, let me go probably to this. So this is the table contents. On this side, I can do some scratch over here, right? So this is the model, and you can think of cutting like this. You cut through between element 1 and the mass at B, and you can also include the support. Okay, there's several ways. You can cut through, remove the support, or here I just do a shortcut here. Okay, this is a shortcut to arrive at the equation of motion in a quick way. But to be really more general, you should really cut off the support, so isolate that element. I may have something coming down later, but let's follow this thought process. Okay, so therefore, if you cut through, remove the mass at B, so over here there must be an internal force, right? You need to remove replace at the cut an internal force. And there's only one internal force in the horizontal direction because we said that there's no motion in the vertical direction. Okay, this is only one dimension, so only one internal force written as F sub B. The subscript B is to designate that this internal force is sitting on the cut at point B. The superscript 1 is belonging to element 1. Okay, that's the notation. Now, for the displacement, this is the force. I'm consistent. For forces, I use red color, red arrow. Displacement, I use green. Now, this is the first displacement, so the subscript is 1, or you can also write as d sub b. to designate that this is the displacement at point B. Using the numerical subscript is also useful when you express all the quantities in matrix form. So numbers are convenient for that. Okay. So here, this is what I just said. Displacement at node B and velocity at node B can be written as dB dot or d1 dot. That's d over dt of d1, and t is the independent variable. So the time derivative, there's only one independent variable. So you can use the prime notation as well. So the dot notation and the prime notation cannot be confused. Typically, later on when we get into partial differential equation, for example, the vibration of a piano string, you have two variables, two independent variables, space and time. Then usually prime designate derivative with respect to the spatial variable or the space variable x, and the dot is used to designate partial derivative with respect to the time variable t. But here you have only one independent variable, and therefore dot and prime doesn't matter. It means one thing. Now, talking about this, I did mention before that this choice of notation D for displacement is not to be confused with the D here. So let me pose this question to the class. This D sub 1 here, everyone knows that's displacement. Okay, the first displacement. How do you interpret the D here in D over dt? Okay, in the derivative. Okay, Anderson. Yeah, derivative, right. But, okay, my question is, can you provide a deeper explanation of the meaning of D? I mean, D over dt, yeah, derivative, but we can also use any other symbol, right? F over ft, G over gt, anything F over t, right?
It's showing that we want to find the rate of change of the displacement.
Rate of change, somebody else here raising your hand, who was it?
I was going to say
Rate of change, yeah, or difference. D is mnemonic for difference, rate of change, difference. So essentially, the difference or the change, in the numerator divided by the change of time in the denominator. Okay? That gives you the rate of change. So D is difference. In D over dt and D over here is displacement. Okay, so everything should make sense. Let me focus your attention to this. Right. So here, F B1. This is again the meaning, right? This is the internal force at point B belonging to element 1. It will be different, if the FB belonging to element 2 will not be the same. So that's why one has to distinguish the internal force at the same point B belonging to element 1 and FB belonging to element 2. Okay, so now let's focus on this one. Now you can express the internal force at B belonging to element 1 as the sum of two quantities. The first is the spring force. And the second is the damper force, right? You see, the first term has K1, and the displacement, dB minus dA is the difference, and dA, if you have the spring in the middle and both points are moving, then you need to take the difference, right, between the displacement in order to find the stretch of the spring. So that's why dB minus dA. okay, or the displacement of point B relative to point A. It's like an observer sitting on point A, and if point A moves and point B also moves, you want to see what's the displacement of point B relative to the observer sitting on point A. Right? But here in this example, dA equal to 0, right? Because that corresponds to the fixed end, right? So the meaning of this first term, is it clear to everyone? If you have any questions, feel free to ask. Okay, any questions or it helps improve the understanding of the class. Right? So once you understand the meaning of the first term as the spring force, then the interpretation of the meaning of the second term should also be clear. I say should, but not entirely obvious, right? If one does not see the relationship between the damper force and the displacement, right? The displacement here has a derivative, so this is the velocity, okay? And also you take the derivative of the stretch, that's dB minus dA, and then take the prime, outside that, because this is a linear operator, so you bring the derivative inside the parentheses. And again, because the displacement at A is fixed, so the velocity at A is also 0. Okay, that's why you have this expression. Critical thinking question: why? Why do you add the spring force to the damper force? Excellent. There's a lot of contribution there. I should not forget. Sorry, you did say something, right? You did contribute. What is your name?
William.
You need to help me here. Once I have the teams, I will have a printout. So could you say that again?
William.
William, okay. And Anderson also. Okay, someone new, someone who is in. Yes, please.
My name's Tony.
Tony, okay,
Yes.
Tony. So so the question is, was why you add, why you perform an addition here? Why?
You want me to answer that?
Yes, please.
All right. What I would think is because the displacement due to the damping would be negative relative to the displacement from the spring force. So the fact that displacement would be negative would kind of account for the fact that it would subtract away. So you can still say you can still add them together, but it would still subtract away. Does that make sense?
The displacement of the damper is
As in, like, the damper would in a way cancel out what the spring force is doing. So when you have your displacement of, say, positive 5 from the spring, the damping would take away maybe 3, so it would be like a displacement of negative 3. So it would still subtract out and get down to 2, but you can still have the addition symbol there to say that you're adding them together.
Okay, so Tony and someone new before I bring up Kyle and Kevin. So Kevin, I think Kyle already contributed, right? And you can all add up together and see. It's like a class collaboration. Okay, so you want to say something? Otherwise, there's a new hand.
Something about them being in parallel or in series.
Okay, something about being parallel in series. Yes.
I was going to say that the damper and the spring were both opposed to motion because the velocity is going to the right. So the damper is trying to counteract that by swinging the other way. And the spring force is, since being stretched, is trying to go backwards.
Okay, both spring and damper oppose the motion. Yes.
I was going to say, isn't it normally like negative kx, and when you do the sum of the forces, you have to move it over the other side and equate this off to the force?
Negative kx. Okay, so what is your name? And
Kenny?
Teddy. Okay.
Oh, the K, Kenny.
Kenny, like the famous saxophonist.
Wow.
Is it? Right?
Yeah.
And Kenny Starr, was it his name? I forgot. And your name?
Richard?
Richard, okay. Yeah, let me move on. There will be plenty of opportunity to contribute. Yeah, so essentially, each of you basically touch on the right answer. If you perform additional cut, yeah. So if you cut here and cut here, you would have for example, this is the spring, and you have the F sub k here, the spring force, and then F sub k, and then you have F sub c here, and F sub c. And then you also isolate this part here, okay? And so here you have several subcomponents, right? Now the equilibrium of this part here. Maybe I should write on my notes so that, because if I write on this, it will disappear. Okay, so if I have written here, then I can add my comments after class and post it to all of you. So if you perform this cut, so here is F sub k, and if you perform let me not cutting here, so that make it simple. Okay, because with Euler cut principle you can cut in many different ways, but however you cut has to be in equilibrium. So this would be F sub c, and then you isolate the other part like this. Okay, and so here you have the force Fb belonging to element 1, because this is element 1 here. Okay, this is element 1. And you have action and reaction, right? So this is F sub k, and this is F sub c. So now this is your sub-component that has to be in equilibrium. Then you do sum of forces equal to 0. Then you can, so sum of forces for this. So let me write the following: sum of forces equal to 0, and that's equal to Fb1, right, minus Fk minus F sub c equal to 0. So therefore, F sub b of element 1 is equal to F sub k plus F sub c. Okay, so that's why you add the two forces together. And so Kevin mentioned something about parallel, because this is a parallel spring and dashpot. But if you put in series, then you cannot add like that. Okay, if the spring is in series with the damper, then it's more complicated. This is simple. Okay, so yeah, so let's move on. So here everything is clear. If you have questions, feel free to ask. Okay? And so once you introduce, at first try mentally to think not to replace dA and dA prime by 0 yet. Okay, write the full expression: dB minus dA, dB prime minus dA prime, and then you apply the boundary condition at A, and dA equals 0 and dA prime equals 0. dA prime or dA dot means the same thing. Then you obtain this shorter expression here, which came from there, where you have only K1 dB and C1 dB. And remember, dB prime means velocity at V. All right, so that's the first free body diagram. William.
I think your microphone just cut out.
Sorry?
I think your microphone stopped.
Oh, I see. Thank you. How much time do we have? Okay. I have a spare battery, so should be a quick operation. Let's put the poles correctly. Yeah, should work now. Hello? Yeah, this is very dangerous. I saw, I don't know if you saw a YouTube video where if you try to throw away battery without capping it, and if the two poles are connected, are touching some metal, okay, it can create fire in your house. Right? Be careful. So either wrap it or put the tape on, or you have this device you want to put on before you throw in the wastebasket or in the drawer. Okay, so we look at the second free body diagram, and let me bring up this. Okay, so the second cut would be like this. Okay, where you isolate the mass. Okay, you only look at the spring and the damper in parallel. So here is the picture. So at the cut, right, at point A and point B, replacing at the cut the internal force Fa. Okay. Oh, I'm still in element 1. I did not move to element 2 yet. So I should go back to this figure here, and I'm not here yet. What I'm doing is another cut, in which, as I mentioned to you before, you can also cut off the support, okay, and look at element 1. It's also known as a free element, because and A is free and B is free, so free instead of fixed free. Okay, so look at that element. And so this is the picture where you would replace at the cut at point A by Fa belonging to element 1. You see K1 and C1, that's element 1, and also the nodes are AB. And at the cut at B, the same thing as before, right? Fb belonging to element 1. And the displacement now, you have dA and dB. Okay, both are functions of time in general. And then this is the general expression which I mentioned before. Before you apply the boundary condition to cancel out dA and dA prime, it should look like this. Okay, where dB minus dA, as mentioned, the interpretation of the difference in the displacement between node B and node A is the stretch, right? It's like you are an observer sitting on node A and look at how much the spring is stretched. So that will be the difference in the two displacements. Because the displacement here is expressed relative to what is called the inertial observer. It's an observer sitting outside in the inertial frame, if we talk about the dynamics terminology. But I think everyone understands that this is the velocity of the stretch, right? So dB prime minus dA prime. Now from this, the derivation of the stiffness matrix in the finite element method follows this thought process, okay, where you have both NA and NB are moving. And the same, once you derive the stiffness matrix for this element, the same thing applies to element 2 and element 3. The only difference would be the different coefficients, spring coefficients and damping coefficient. So the thought process or the principle remains exactly the same. Okay? So that's why it's good to do this alternative level here. Now, if you, again, Euler-Cut principle, right? This element has to be in equilibrium. So sum of forces in the horizontal direction equal to 0. That gives you FA1 equal to minus FB1, right? Because FA plus FB has to be 0. So FA is equal to minus FB1, okay? And FB is already here. Okay, so therefore the internal force at point A of element 1 is opposite in sign, in direction, to the internal force at B of the same element 1. That's what it means. And so here you just have minus dB instead of plus dB, and plus dA instead of minus dA, and the same thing for the derivative of the spectrum. Okay. So now let's put together. So now you have two expressions. Okay. Let's focus your attention to this first. You know, these two expressions here can be written as follows. So first, write the internal force at A first. You know, A happens before B if you go from left to right. So FA first and then FB second. Right? That's how we number the nodes. We go from left to right. So if you rewrite the expression for FA of element 1 as K1, now instead of minus dB plus dA, write as dA minus dB. And the same thing for the time derivative. So dA prime minus dB prime. But for the force at B, for the same element 1, then you rewrite, instead of dB minus dA, you write as minus dA plus dB. And on this side, the same thing for the time derivative. So damping coefficient times minus dA prime plus dB. Then you can put these two expressions in matrix form as follows. Right? let me erase the. Can those in the back see the formula down here, or should I erase? You can see. Okay, now it's important for you to be able to derive this expression, this matrix form, from these two equations. And this involves knowing how to multiply a matrix and a column matrix, right? A 2 by 2 matrix and a 2 by 1 column matrix. Okay? 2 by 2 is, the first number is the number of rows. Right? So 2 rows, 2 columns, 2 by 2. In this matrix here, it's a column matrix, 2 rows, but 1 column, so 2 by 1. Okay? And the multiplication, matrix multiplication, is you take the row times the column, right? That gives you the first component. Okay, so let's follow this thought process here. Take the first row times this column, give you FA, right? Let's check. K1 times dA minus K1 times dB. K1, up here. K1 times dA minus K1 times dB. Check out. That's the first term. Okay. Now let's check the second term over here. Right? So second term of FA. Okay, so that's the top row, row number 1. So C1 times dA prime minus C1 times dB prime. C1 times dA prime minus C1 times dB prime. Let's check out. Okay. And then you can verify that the second row also give you this second equation. Right? That's one more time. Let's take this second row here, multiplied by this column, minus K1, so FB, the first term, right? The spring force, minus K1 times dA plus K1 times dB. Minus K1 times dA plus K1 times dB. check out. And found. And then the second term you can verify. Okay, so please review matrix multiplication. Is it reasonable to assume that matrix operation is known? Okay. Don't hesitate to ask if you have questions. Let me see how much time. Okay. All right. So once let me avoid overloading information. So let's use the mask. Okay. Once you have the matrix, this is called, by the way, force displacement relation. This is called the force displacement relation. It's basically the equivalent of F equal to KD. Okay, but more complex, more advanced. You need F equal to KD, but now you're talking about matrices. Okay? Now this matrix here has a name. It's called the stiffness matrix. Okay, get used to that terminology. That's used in finite element. Now this is called the damping matrix. The first column dAdB is the matrix of the displacement, and the column of dA prime and dB prime is the matrix of the velocity, velocities. Okay, in plural. And then the next step is to apply the boundary condition, right? dA and dA prime equal to 0 because point A is fixed, and you get the same equation as before. So from this more general approach, you also get the same result. That's why I said at the beginning that I took a shortcut. When I performed the Euler cut for the first element, I included the fixed boundary condition at A. But this is a better method because once you derive this relation here, it is applicable to element 2, element 3, and more. If you have a million elements, it's the same relation. Yes.
What are situations where you can use that shortcut? Just when there's supports on the end of a
What is the situation?
where you can use that shortcut where you knew that dA was going to be 0.
Yeah, so you see that here, or maybe better yet, a picture that I already drawn here. You see, because I was focusing on developing the equations for mass M1 and mass M2. So I say, okay, let's include the support because then I implicitly eliminate the displacement A. But I think you can do the more general way as well. That's what I would advise. Okay. Yeah, so does that answer your question? So that means the following. That means that you can also do the same trick over here. You can also include the support, and in fact, that's what I would be doing, I think. I don't remember, but you can also do like this. Okay. That way you, let's say, implicitly or explicitly, whichever way you want to mention, include the boundary condition at point D, so that the equation would only involve the force at the cut at point C. So that's I think with that, it's usually I leave the last 5 minutes, 3 to 5 minutes for the team to write the lecture summary. And like I said, lecture summary is also a way to convey to me any questions that the team may have during the lecture. Okay, so now I think we can stop now and continue.